Okay, welcome back to this video. So we will go through the CAD exercise 9. So this video we will go through about transient noise simulation. So this is very useful simulation setup for checking circuits noise that includes the thermal noise of circuits and flicker noise of circuits. So this is an independent noise source from the quantization noise from ADC. So so here this is I think this was some parts are straightforward and clear. Some parts might be a bit confusing. So let me add some more comments about this. So virtual source built-in noise analysis can be applied when both input and output or output only. So there are two options for the noise analysis I will go through as well. So noise input goes to some circuit, we get output, then we can wrapper to the input. So wrappers to input noise or input wrappers noise. We can calculate this. The second option is that there's no input, but there is some circuit and it generates some output. Then we can measure output wrappers noise. So both of them are built-in noise analysis in Cadence Virtuoso. And this is actually based on the AC signal, which is a small signal model that we normally verify, like applying the power spectral density model of the transistors or resistors and so on and so forth. But in ADC, for example, the output is actually digital code. So it's not a small signal, the waveform. The waveforms or data at the output are actually digital. It's not a small signal, analog signal. So standard noise analysis cannot be used. So in this case, we have to first run transient simulation that is actually considering the circuit noise. That is, there is some option to turn on circuit noise or turn off circuit noise. So by default, the transient simulation runs without circuits, thermal noise, circuits, flicker noise, and so on. But in transient noise simulation, now we have to think about how to process this data in terms of running FFT. Okay, let me erase these annotations. So transient noise simulation runs for a duration of basically this. So probably you are familiar now by this point, T trend, which is a transient simulation time. And it is defined as the number of data points for transient simulation and the step size of the time. So when you run transient simulation, let's say we have sine wave, then this sine wave is formed with some data point like this. Like this. So this is assuming that the data points are uniform. This is assuming the data points are collected uniform. But by default, when you run transient simulation, you will find that more dense data point here and a little bit sparse data point within this range. So it runs in a way that the collected data points are more densely connected near slowly changing signal and fastly changing signal. It collects the more sparse data point. But we are assuming that we are collecting data in transient noise simulation. When the noise option is turned on, then we assume that it is uniformly collected data points are there. So in this case, well, according to sampling theorem, when you collect data by running this simulation, anyway, this is a simulation engine that is based on samples. So those are samples actually. Samples and samples and so on. So that means it is under the theoretical theoretical limit of Nyquist sampling theorem, right? So this is some sort of sampling frequency. Then this is, let's say this is fs, and this is equal to 1 over f step. Let's say this is a sampling period of our simulation engine. Then the sampling frequency is f step, and this is actually what we have learned as 1 over fs, which is sampling frequency. But this is a simulation engine, so let's call this as a f step. Then the bandwidth of the transient noise, the bandwidth of the noise in transient noise simulation is defined as half of this step frequency, according to Nyquist theorem. So other noise sources, other like signals, are actually just aliased back to the baseband, which is a signal band, right? So according to this step and f step relationship, we can collect this relationship 1 over 2 times t step, right? And then for n trend, we have to consider some sort of settling time plus the data points we are going to run FFT. So let's say like we are running sine wave, simulation. But let's say there is some settling behavior like this. For example, T transient simulation. And this is, let's say, voltage or data out. But then we don't want to run FFT in this region because this is an initial settling. It will make the simulation or FFT output a bit incorrect rather than our theoretical expectation. So we want to cut this out. So this part is we can call T settle, initial settling, or the number of settle times T step. So what I want to say is that we don't want to include this part, T settle. So let's define an n transient simulation, the number of data points for transient simulation, which is settling time plus FFT, which is the amount we actually want to run FFT. So for, let's say, FFT. Then by plugging in this equation and this equation here, and this equation here, then we can collect the final equation. Transient time is actually defined as this is a noise f max here. I think this is a f step. F step, T 2 times F step is a denominator. For the numerator, we have settling sample number and FFT sample number. This is in the end defined as a T settle plus T FFT. Okay, but what is noise Fmax? What is Fmax? This is what we call as here Fn bandwidth. So within the simulation on running engine, we call this one as a noise Fmax because within this, let's say this is a frequency domain, frequency axis. Within this Fn bandwidth, which is a noise bandwidth according to our simulation engine, there will be noise, but for both all other data points, here, maybe here, those are all aliased back to our noise bandwidth because there is a limited sampling period of our simulation engine. So this is a theoretical limit, and we call within our transient noise setup, we call noise Fmax, which is a parameter name. So we have to define this noise Fmax, which has a relationship in this T trend 2 times noise Fmax NZ2 plus NFFT. And then this is the noise fx. So what about f low side, which is noise f mean. So this is a noise f mean is actually defined. Oh, this is again. And then there is a finite limit of minimum frequency. So even if you want to run transient noise simulation up until like, let's say DC frequency, like 0 hertz. Of course, there is a DC offset, but let's say well, I want to find 0.1 hertz frequency. Then this kind of 0.1 hertz is very slow. Each one period time is like 10 seconds, right? But we are running for, let's say, like 1 megahertz clock. Then this kind of one period TS is indeed 100 nanosecond, right? So there is a huge amount of time difference. So in the end, for running FFT, we cannot actually plot here. We cannot actually plot the frequency, which is less than 1 over TFFT. So because when we collect the data, let's say we are running FFT within this window, then we can collect the slower signal than this time window. This is a theoretical limit, right? So definitely there is a limit for this minimum frequency we can plot within our FFT output waveform output result. So an FFT is defined as an FFT has a relationship between 2 times noise fmax here, 2 times noise fmax, and we are cutting this part only. So TFFT is equal to NFFT over 2 times noise fmax. So 2 times noise fmax is indeed, this is, let me see the FFT. Yeah, so NFFT, 2 times noise fx times TFFT. So which is equal to 1 over noise f mean. So here, delta f. So when you run FFT, there is a certain minimum frequency resolution for delta f, which is defined as a noise f mean. So minimum frequency of running a noise simulation or FFT. So this is a background. Of course, you might feel confusing, like there is a lot of different notations used here. I mean, why do we need to define noise bandwidth, f step, and noise fmax? And those are all referring the same thing, which is noise fmax. In this case, we are defining TFFT and like delta f, noise f mean, and those are all related to actually the same thing, which is minimum frequency f mean here for running FFT. So these are indicating f max for running FFT. But there is a notation used in simulation engine only, and there's notation used in our practical research or practical communication when we talk about FFT and noise analysis. So it is better to understand everything here used in this document. And another thing I would like to highlight is that yeah, so here, let's say we are running sampling frequency is equal to 1 megahertz. Then, if our noise maximum frequency is up until only like 1 megahertz, which is noise Fmax, then there is almost, there is almost no frequency to alias back. In this case, let's assume that there is a noise that is inserted into ADC, and it is operating with a certain sampling frequency. Then, if this noise is band limited, it appears like it is applied with anti-aliasing filter already. So, to accurately measure what is impacting to the ADC, to accurately model our circuit analysis situation, it is better to set noise Fmax for running transient noise simulation way higher than the sampling frequency or Nyquist frequency here, noise Fmax. But in this case, if we increase noise Fmax, then we have to run a lot of transient noise steps, which can make your simulation time slower and slower and slower. So this is for example, let's say we want to run T trend for 1 microsecond. Then let's say we have T step and so not equal T step and times and trend. So in this case, let's say we want to run for 1 microsecond. This is a fixed. Then if we reduce this T step by increasing noise Fmax here, then we have to increase the number of data points we have to collect to satisfy the same simulation duration. And this is actually what is impacting our simulation time. So when you run the simulation, then there is a 1% and 2% and so on and so forth, and 100%, that simulation is done, right? Then in each 1%, it will take you larger simulation time, for example, right? In extreme cases, even running 1%, it can take 1 hour. If you set T step too small compared to the entire time for running transient noise simulation. Certainly, there is a trade-off. Okay, then this is a brief explanation about this background. So I will go through running simulation of very simple register thermal noise. I believe all of you have studied about the noise basics of the noise background or theoretical background of noise in circuits in basics of IC design course. So I think I can open this one. Okay, I was simulating another circuit. Here, let me delete. All right, so yeah, you can build the same setup like this, and let me see. DC voltage 0 volt, and we are setting VSS, and let's assign the name R noise. So then in this case, we can run simulation. So here, it is just some background of thermal noise for the power spectral density of one register. It is defined as a 4kTr, right? As you can find other textbooks or materials from Basics of IC Design course. And yeah, so if you assign 1 kilo ohm for R, room temperature, which is 300 K, and here small k is a Boltzmann constant, so constant value is here. Then the noise density is actually indeed approximated very theoretically popular number, which is 4 nanovolt per square root hertz. And then if you want to calculate root mean square, then yeah, you can basically multiply this one by the bandwidth of noise you want to calculate here. So multiply each other and take the square root. Then you get the RMS value. Assuming that we are applying the ideal low pass filter. If there is one pole low pass filter, then there should be a multiplied with noise bandwidth vector, which is pi over 2. All right. So let me see here. In this case, we can run simulation about transient noise simulation. But before that, let me show how to run noise simulation without running transient noise simulation. Just for example, let me assign like 1 megahertz to 1 gigahertz and output noise. We can change the voltage. Positive output node is here, click, and negative output node, VSS, click. And input noise, we don't have any input port. So this is a typical case of we have circuit, which is R, and there is no input, but there's only output, which is a generating noise. So I didn't assign any input, and yeah, so in this condition, we can run the simulation. Okay, so you can go to output noise, volt per square root hertz, magnitude, and click the plot. You can find that it is approximated. Of course, there is some sort of 4.07. It's not exactly same as 4 nanovolt, but it is approximated to 4 nanovolt per square root hertz. Here. Okay, at this condition, let me set up the transient noise simulation. So, first thing, of course, is defining transient simulation stop time. Let's select conservative. Let me first apply. And you can enable, as shown here, you can enable transient noise. And for the noise fmax, as I said, noise fmax assign here. And as shown is here, transient noise options, noise fmin, assign noise fmin. Okay, click, and noise contribution turn on, and select this one. Okay, this is selected with green box, and press the C. Okay, and yeah, that's it, and apply, and okay. And by the way, it is important to make sure you turn on this generate noise option. Yes, this is because this is an idle register. So yes, and probably if you use other PDKs or process technologies, there should be or there can be some options. By default, the generate noise option is turned on, or if it's not turned on, you need to double check to make sure it is turned on in your simulation setup. And then yeah, so we collected here. So what you need to feel is according to this relationship, you need to fill this one. So let me define T setter first. T setter, which is set time. In this case, yeah, we can assign just 0 because it's just one register. There's no such a dynamic circuit or there's no such a filter circuit. So there should not require any settling time for this register. And the noise fmax is indeed here. Noise fmax is here. And then let me see. Where can I find noise fmax? Noise fmax, TFFT. Oh yeah, so we need to first define how many data points we will run. So next. How many data points we will run for FFT and FFT? For this case, as I indicated here, you can assign 2 to the power of 16 here, that, and T set 0 and noise F min computed from equation 2, noise F max. So now we are setting maximum frequency we will see for this noise generated from register. So in this case, well, you can assign like 1 megahertz, like 10 megahertz, or 1 terahertz. It's up to you, but in my simulation setup, I will just decide as a 1 gigahertz as the maximum frequency I want to check for the noise. And the noise minimum frequency, this is indeed limited by here, this equation, according to Nyquist theorem. So 2 times noise max divided by n and t. This is it. And yeah, so this case, the n FFT over 2 times noise F max, which is equal to noise F min, or 1 over noise F min, and plus T settle. Yeah, okay. So I think this is done for the simulation setup. Let's run the simulation. Okay. So transient noise, and if you plot our noise, we can see that the output is now fluctuating here and there, here and there, here and there. So by comparison, if I disable this transient noise simulation, okay, then let's see what happens. Okay. Yeah, right. You can see that there is no change, even if we move this plot, and even if you zoom in, of course, there should not change anything because there is no noise modeled during simulation setup in this idea. This is an ideal register. There should not any fluctuation. So ideally, and yeah, so let me delete this one and go back, turn the noise, apply, and run the simulation again. Okay, and if you press Ctrl R, then it refreshes. Okay, for plotting the noise spectrum density, PSD, the noise power spectral density, yeah, so you can go through this tutorial wise on this guide. But before that, let me double check the RMS noise. So you can go to calculator here, just type RMS, then RMS, and calculate. So 127 microvolt RMS. And indeed, if you go up here, then this document already calculated the noise RMS value. So for noise bandwidth equal to 1 gigahertz, then there is a 1 gigahertz noise bandwidth, resistance 1 kilo ohm, 300K, which is the room temperature. It's set as a room temperature here, and Boltzmann constant. So it is approximated to 128 microvolt. So it's quite close to our theoretical expectation, right? 127 microvolt RMS. And then for plotting the noise power spectral density, you can follow this guide. So first thing you need to do is just click, select this one, go measurement, spectrum, and now you have to fill this setup. Variable T settle, because we don't want to include settling time. So in this case, I didn't set any settling time, so it is equal to just 0. But it is a very good habit to make sure you are considering settling time here. And for the NFFT, it is 2 to the power of 16. So what is 2 to the power of 16? Well, you can calculate here 2 to the power of 16. Oh, 6554 e to the power of 3, which is not I expected. So you can calculate later, but this is, oh, maybe we can use this one later. So we pick 2 to the power of 0. So this is 65,536. So 655 is this. Okay, and by pressing this S button, so this changes to 1 giga, which is as we expected, noise fmax, right? As we set as a maximum frequency for noise. And then yeah, the later thing we have to do is now disable this FFT and enable ESD. So what is the difference? So previously, up until last CAD exercise session, we used FFT, but now we are using PSD. So the difference is that for FFT, for running FFT, the frequency unit for one data point to another data point, this frequency unit, delta F, is indeed 1 over n FFT for running FFT. So this is result of FFT unit for the time frequency resolution. But power spectral density is indeed normalized by 1 Hertz. So unit for FFT is, I think, unit for, I mean, not units, how I say, the frequency resolution unit is being, which is equal to here. But for power spectral density, this is indeed Hertz. So the y-axis, Hertz means this is 1 Hertz. And the y-axis is 40 square Hertz. This is a power spectral density. So we first compute FFT and then normalize over entire frequency such that it can output 1 Hertz normalized power. So that is the definition of power spectral density. And as you can see, for noise analysis, we are using both per board per square root Hertz. And as I said, for the power spectral density, it is per square normalized, 1 Hertz normalized power, right? So when you calculate power spectral density and then take the square root, then it is equal to board per square root Hertz. Okay. And and then what is this window size? So window size is that we are learning power spectral density for how to say the segment. So if we set this window size as same as sample count, which is a number of samples, exactly same, then we are running FFT for entire samples. But if you set window size smaller than the number of samples used in the simulation setup, for example, as indicated here, 64, I set 64, then what happens is that we run FFT based power spectral density, and we run FFT based power spectral density, and so on and so forth here. And this is 64. And previously it is 65536, 64. So difference is that for each for each learning FFT window, then we are learning this amount of FFT, this amount of FFT, and then we do the averaging. FFT result, FFT result. So we do the averaging. So this kind of fluctuating, noisy output can be averaged out to less fluctuating. So let me show you what it look like. So if I run it, 65536, 65536, and select append, then this is the power spectral density. And then if I do square root, let me see here. Okay, before we go to this part, oh no, we can do this. Let's go to t square root and plot it. Yeah, then you can see that, by the way, so the y-axis is different. Even if we are plotting here, the y-axis for our resistor noise is here. Our green curve is here, and our red curve for power spectral density is right side here. So unit is different. So in this case, it's better to match a unit with, for example, 4 nanovolt to 4.5. So if I set 4 nano, 4.5 nano, then you can see that it is fluctuating a lot, even if it cannot fit into our window, right? So let me go back to auto scale. Then you can see this. It is very much fluctuating. So this is because the number of data points are a bit limited, even if we are running very large amount of FFT point here. So in this case, what we can try is that we are computing this chunk and this chunk. Let's say this is a 50% of data point. This is 50% of data point. Then for running FFT, it looks like random, right? So for running FFT, the randomness will make sure that maybe it will be different like this. Like this. So you can see that there is a peak. But for running FFT, let's say there is one giant peak at this frequency within this window, but next window, maybe this peak will be the other way down, like peaking at this point or less peak. Then this peaky, the data points can be kind of averaged out. So we want to calculate the average baseline of the noise power spectral density. So that is the intention. Of course, when we cut, for example, 50% and 50%, then definitely the F mean, the minimum frequency we can run the FFT is reduced because this is faster than the entire window for running FFT. So minimum frequency will be reduced, of course, but we can average out this kind of fluctuation, and it doesn't necessarily actually, how can I say it? It doesn't necessarily exactly align with the end-to-end. So, for example, there is another method for calculating the averaging out, like this kind of overlapping. Overlapping method is also existing. So even if it is not shown here. Okay, so for example, 2 to the power of 10 is 1024. Then this entire window is 2 to the power of 16. So now we are computing 1 FFT as a 2 to the power of 10, and there can be 64, which is 2 to the power of 6 amount of small chunks are there, small segments are there. So we are calculating FFT for 2 to the power of 10 data points and then averaging out. Then let's see what happens. Append and plot. We don't want to repeat this every single time. So let's save it to ADE and let's say noise SD. And for the window size, yeah, and this is an FFT. So I'll do variable with FFT, change, and let's see if this one works. Oh, it doesn't work. Then there's no choice. Sometimes it doesn't work. Then we have to manually do this and go to calculator and SQLT here. Okay, so now you can see that it is much, much cleaner, right, compared to red curve and yellow curve, right? Because we averaged out over multiple segments for running FFT. But you can see that its minimum frequency is increased here, from here to there. So this is some effect of what we are calling noise FMIN. Of course, you can do even further, for example, as shown here in this guideline. Well, you can try 64 or maybe 32, but definitely you may lose the frequency resolution and minimum frequency limit, SQRT. Then you can see that it is much, much cleaner compared to red case, yellow case, and green case. So we are running FFT over randomness. So that is the reason why we need this kind of average. So let me delete, and apply align y-axis. So minimum was 4 here, and maximum was 4.5. Apply. Then, okay, let me see what is happening. Oh, no. Okay, then you can see that. So now the y-axis is aligned, but there is some still zigzag fluctuation, and the minimum is not up. So let's say it 3.5. This one also 3.5. Then you can see here, this is quite close enough each other. So this is a noise, small signal based noise analysis result. So this is a transient noise analysis result. So there is some discrepancy, but still quite close each other. So there is also some note, pulse vector density versus FFT here. And if PSD plot is too jagged, so this is a too jagged. For example, our red case was like this, right? Red curve. If it's too jagged, then reduce the window size. It is a recommendation. Okay, then I believe we have to go through all deliverables. And yeah, the next step is that for running transient noise simulation, this is also a possible solution. But indeed, we can model this using some method of Verilog-A. So Verilog-A is kind of language used in cadence virtuoso to describe analog circuits using kind of similar to Verilog grammar. So you can download VerilogA script for our noise generator. So you can go to GitHub here. Oh no. Let me go back. Okay. I think this is, yeah, so this is the website for our course GitHub. So here, noise gen VA. .va means Verilog-A. So for Verilog, it is .v, which is Verilog used in digital circuit. For system Verilog, it is SV. For Verilog-A, it is .va. Anyway, so you can go to here, VA, and yeah, so you can use this directly. So we have noise source, noise SRC. Then, so yeah, normally you select schematic, right? You can go down and then click Verilog-A, Verilog-A. Okay. And yeah, so noise SRC, you can simply copy and paste, save it. Yes. It's just asking, do you want to create a symbol? Yes, of course. And just click. So yeah, so now it is generated. So what it does is that it has a plus port and minus port, positive port and negative port, and there is a noise generated between this voltage plus and minus voltage. There is a noise generated. So if you assign a negative port as a ground, then you can make positive port as a noise generator. But this is a bit different from ideal noise generator from our, for example, AHDL. I think there is also noise source here. So this is a bit different. So noise source, I think, let me see. Noise source and amplitude. Yeah, amplitude. So this is amplitude based, and this is an approximate white noise source, and amplitude of the output signal about around 0 volt. I think this means mean value is equal to 0 volt. And yeah, noise random seed and times maximum integer kind of amplitude. And yeah, so what I want to say is that this is not theoretically modeling the behavior of what we call noise power spectral density. So this new example, the Verilog-A script, is that we are adding here noise and V for each data point, 0.5 over bandwidth, which is at each data point, random noise distribution with square root bandwidth, which is adding as the value of noise power spectral density, so noise density here. So this, we are considering voltage per square root hertz, which is more useful in analog circuit analysis, noise analysis. And then we can make this symbol pretty. So if you go to analog only, go to VDC and open read only, then we have this, and you can simply select this one and then copy, paste. Then we don't want the existing port. P N and delete. Of course, you can leave the cell view name and what is it, the other parameters, but this is just a noise generator. So let's assign it as a minimal. It's up to you. And then noise source here, yeah, looks like quite similar. This is too similar. So let me add one more side note. It's quite too, as I say, it may be confusing to distinguish which one is which when we add noise source and the VDC. So you can add node by pressing Shift N, Shift N. And here, let's assign, the text as a noise. So you can put here and maybe this way. And I prefer to use Euro style. It's up to you. And then center, center. And noise. Yeah, that is easier. And assign VSS. And let's say Verilog-A noise, for example. Yeah. Or, okay. Display. All right. And if we go back here, and now we have completed up until this step. In our test bench, it was guided to replace 1 kilo ohm, but let's leave it like this. And if you go here, then you can change the noise density value, which is 4 nanovolt per square root hertz. For example, as we saw here, 4.71. You set 4.071, sorry, 0.71, and the noise bandwidth is defined as 1 gigahertz. For example, this one can be set as a noise less. Okay. Then in this case, what is good is that now we can run noise simulation without enabling this transient noise, which is very, very good and advantageous because when you turn on this transient noise setup, then normally it takes your simulation time slower. So which is very, very useful if we can make use of this kind of noise modeling. And let's run the simulation. Okay, looks like it is completed, but let me see. Let me double check if there was any. Okay, there's some error. So in this case, it is better to check project directory here. There is a Aalto simulations, which is we don't use Aalto setup. So in at Aalto University, we use this folder as a noise simulation files. Not this one, uh, simulator. Yeah, here project Aalto simulations here. So it will be different when you try to design in different environments. For example, in other universities, it's set up. I mean, its simulation files will be stored in different paths. So you can find where it is stored if you happen to see this kind of error. So let me go to this simulation uh, setup and to make sure. Yeah, we don't have any other choice. We have to close it. And basically, you can remove it because this is a simulation data. It's not important design data. It is just a simulated data. And then after removing it, go back to register. Yep. And I think now it is clear, right? Because we removed simulated data, so nothing is left. And I believe if we run the simulation again, it can run correctly. Okay, good. All right. So if I plot this, oh no, sometimes it should go to main form. Okay, or the noise. Okay, now you can see that it has a similar situation that we have seen in previous simulation. So for example, if I go back to transient noise enable, apply, and let's run the simulation. And here, so we have transient noise simulation based register noise, and this is a Verilog-A model noise. It looks like the scale is similar each other. Of course, its peak-to-peak value is different. So if we calculate root mean scale, or root mean square, RMS, then let's see what happens. RMS and plot, which is 127 microvolt, as we checked. And if I plot VA noise, then it is also 127 microvolt RMS. So its RMS values are quite similar each other, right? And if I also plot as a comparison noise, output noise plot. This is a register output noise. So yeah, let's try to calculate its noise spectral density for this Verilog noise source. Variable the sample here and variable T trend. Also, by the way, so the reason why I removed this simulation setup is that there is some remaining data left in simulation cache, and that is making conflict that made us to run a simulation incorrectly. So if you happen to find this kind of error, then it's good to refresh the simulation engine's cache data. So this is before, as we did, append, plot, go to calculator, SQRT. Okay. Then you can see that is level 3.5 apply is quite similar as we have seen in previous setup, right? Now it's quite similar. This is a VA noise result, and so this is a VA noise, right? If I replace this one as a R noise, then yeah. So this is a transient noise simulation result of thermal noise from register, 1 kilo ohm register. This is a Verilog-A modeled noise result for replicating 4.07 some volt that can mimic 1 kilo ohm resistance thermal noise. And this is a small signal based output noise, which are quite close enough. Okay, and RMS we have also checked. Now we can move to enough verification step.